Good morning, everyone, and thank you for joining us this morning. 10 a.m. seems earlier now than it did when we scheduled it earlier in the week. But thank you very much for taking your time out on Sunday morning to join us for another of our Saints Talks. These are short presentations by leading members of our academic community on subjects we hope are of general interest. It's taking place on a Sunday because, as I'm sure you know, it's part of our first virtual alumni weekend, and if you'd like to see more of the events that are happening today, we're going to drop the link to the program into the chat bar, so you can have a look at that. My name is David Williams. I look after the alumni and supporter relationship with St Andrews, and I'm delighted today to be introducing you to Dr. Hooley. Dr. Hooley got his PhD from Oxford and then did postgraduate research at Rutgers University in the USA and at the University of Birmingham here in the UK. He is now a senior lecturer in theoretical condensed matter physics. His research concerns the development of quantum theories of large ensembles of particles, and this applies to many areas, includes nanotechnology, the physics of ultra-cold atomic gases, quantum computing, and even phase transitions in the early universe. Dr. Hooley will talk for about 20 or 25 minutes, and then we'll have about the same amount of time for questions afterwards. We'll aim to finish about 10 to 11 Scotland time. If you do want to ask a question, you can type them into the chat bar, and I will ask them to Dr. Hooley at the end. Thank you again for joining us, and over now to Dr. Hooley for his talk.
Excellent. Thank you very much, David, and thank you to the organisers for the opportunity to talk to you today, and thank you to the audience for turning out at 10 a.m. Scotland time, or whatever time zone you're in, on a Sunday to hear this. My name's Chris Hooley, as David said. I'm an academic staff member in the Centre for Designer Quantum Materials at the University of St Andrews, and this is today's date. So the plan of the talk is the following. I will say something briefly about the ubiquity of electronics. I will say something about how electronics works, and I'll take an early example of electronics, the telegraph, as my illustration of that. I'll then talk about some of the developments that happened in the 20th century, automating the processing as well as the transmission of information and the birth of the modern computer. Obviously, there are things that look a bit like computers that go much further back than that. I will say something about the fact that our transmission technologies have now changed to some extent, at least for long distances, but really I don't want to talk about transmission of information over long distances. I want to talk about the transmission of information that happens inside the working computer and the processing of information that happens inside the working computer. And what I really want to address, in a sense, the core message of the talk is that the way that we currently do transmission of information and processing of information is actually quite energetically costly. Data storage and transmission is already a few % of the global carbon budget. And as we clamp down on other sources of carbon, that figure seems as if it's going to rise considerably. My colloquial way of expressing that is to ask why your laptop needs a fan, and I'll explain why that is. But the fact that computers get hot when they operate is actually becoming really important as a wastage of energy now that there's so much computing around. And in the final part of the talk, I'd like to discuss some current proposals for how we might go beyond the way we currently transmit and process information into a technology which is in principle almost infinitely less wasteful of energy in the transmission and processing of information, and that's spintronics for the transmission and quantum computing for the processing. And I'll say more about those when we get there. Of course, the point really is that one needs new physics for new technologies. So to achieve the kind of information transmission and processing I'll be discussing, we need to think about developing new materials, and we need new physical theories, or developments at least of existing physical theories, to describe what goes on in the interiors of those new materials. And that's sort of the work that we actually do. I won't go into huge detail about it because this is supposed to be a public access talk, but I wanted at least to give one motivation for why we should even think about new materials, and in particular quantum materials. And then it will be over to you, and I will be very happy to take your questions. So let's begin with an observation that electronics is ubiquitous. I probably don't need to stress this point. Laptops, smartphones, gaming consoles, and also even in things that, a few decades ago it would have seemed strange to think that we would have computing technology in our ovens, but in fact that's now become quite standard. We have computing technology in our cars and so on, and even domestic appliances and the smarter type of headphone and so on. It's worth asking, why is that? So if one looks at economic output, this graph is labelled England, which is perhaps a little misleading. It's actually the UK from 1700 onwards, which is when all the action is happening. If we had a similar graph that went to Scotland before 1700, it wouldn't look a lot different from this. And what you see is that there's been a dramatic takeoff in economic output over the past sort of 2 or 3 centuries. And a lot of that work in the modern age is really the processing of information, be it financial transactions or various other types of information processing task. And we have started to increase efficiency in all sorts of aspects of economic activity by deploying modern electronics, which is just immensely quick compared to the teams of people sitting at wooden desks that we had doing this kind of information processing task 100 or 150 years ago. How have we managed to get electronics into so many aspects of our lives? Well, it's really a story about miniaturization. 80 years ago or so, this is what a computer looked like. In fact, this is what computers look like, in the sense that the women in this photograph would have had computer as their job description. A computer used to be a title for a human activity. Then we made mechanical computers, which were mechanisms that did what human computers used to do. And now we associate the term computer exclusively with the mechanical versions. But for a long time, it was really a hybrid. There were, the computer could do bits of calculation, but configuring which calculation it was going to do required the intercession of a human. A simple way of thinking of that is it's a bit like a telephone exchange. In the old telephone exchanges, a human operator was needed to plug in the connections that connected one caller to another, after which the mechanical part would handle the transmission of the sound, but there was a need for human kind of intervention to set up the routing of the signals. A really important thing happened in the mid-20th century, which was the development of this device. Now, this is a very crude early prototype of a transistor. And the crucial thing that a transistor does is allow the human in that telephone exchange to be replaced by a computer effectively reconnecting its own circuitry. A transistor is essentially a method by which a computer can reconnect its own internal wiring on the fly, as it were, without the need of a human being unplugging things and plugging them in somewhere else. And I mean, now we can put millions of these transistors on small chips of silicon, and this is the workhorse of modern digital computing, and these chips are all over the place. So I want to tell a little bit about that story and to talk about how the information moves around inside chips like this and what some of the problems are with that. And the problem is effectively heat generation. So just to set the stage, I want to point out that there are 3 pillars really of electronic computing, all of which we need to have in order to make today's information processing systems work. The first pillar is storage. We need to be able to keep information safe, usually in one place until it's needed. That started with local storage to the computer, cassette drives, floppy disks, then hard drives, another great success of materials physics, by the way. And then it moved on to things like cloud storage, where the information is kept in huge data farms and is just piped to us through the Ethernet whenever we want to get hold of it. And it is remarkable when you think about it that our transmission connections are now so fast and reliable that we don't need locally stored copies of anything that we use, essentially, even when it's megabytes of information, because more or less at the snap of fingers, we can grab it out of the cloud. Transmission is therefore also very important. We need to be able to move information around, and that can be over long distances. You know, I could be downloading a movie from a data farm in Texas, or it could be over short distances, such as inside the microchip itself, moving bits of information around in order to process them. And that brings us to our third pillar, which is processing. Of course, the whole point of computing is to take existing information and generate new information, actually do some calculations. And so that's combining existing information to make new stuff. For example, very simple example, adding two numbers. But actually, inside the guts of it, that is what your computer is doing. It is shuffling numbers around, adding them together, manipulating them in various ways, and then flinging them out to some device like a monitor or a speaker to generate the image or the sound that you see. And it's worth thinking about the fact that the computer on which you're watching this and the computer on which I'm broadcasting this are doing that now at the rate of billions of such calculations per second. Great, so let's step back, because having illustrated that content of computing, I'd like to say something about what's really going on at a physical level when a computer operates. And the easiest way to think about that is to zoom out to much larger scales where it's easier to see what's going on. So let's step back in history to the 19th century and talk about the telegraph. This was a revolutionary method of long distance information transmission based on electromagnetism. Here is an early telegraph set. You have an operator at one end with a key who can send little beeps down a very long transmission line, which are received then at the other end. For example, one could encode a message in Morse code, and it could be received at the other end and transcribed. How does a telegraph basically work? It's fundamentally like the experiment shown in this picture. This is a still from a video. We have a rope, which is the medium which is going to carry the information. We have a person at one end of the rope who shakes the rope. It is in the nature of the rope that a wave created at one end will propagate along the rope. This is to do with tension and mass and physical properties of the rope. And that wave arrives at the other end. And so the other person can see, in the simplest case, that there is someone at the far end of the rope who is sending this wave down. If the rope is kept under very high tension, then one can actually send individual pulses along the rope. And effectively, a telegraph is just a version of that, where the rope is replaced by a long metal wire, but we are still sending little wave pulses down that wire, and they're being received at the other end and then transcribed. What is inside the telegraph wire? Well, like all materials, the telegraph wire is made of atoms. Actually, more strictly, the telegraph wire is made of ions, so those are positively electrically charged, and then their negative electron counterparts are kind of floating around freely in between. So here are a couple of examples of the structures that those positive ions take or might take inside a metallic solid. And it's important to appreciate the scale here. So this distance is about half a nanometer, which is half of a billionth of a meter. Just to get across what kind of distance scale we're talking about there, if I took a block of copper that was a meter along each side and inflated it until its individual atoms were a meter apart, the block itself would fill the gap between the planet Earth and the planet Venus. So this is a very small scale, which is why, of course, we didn't really find out about the existence of these atoms for quite a long time. But now we're quite confident from X-ray scattering and so on that this is what the interiors of solids look like. But most importantly, as well as that crystal of ions, we have a fluid of free electrons, and it is those free electrons that carry the signal through the metal. Every physicist knows that electrons should always be drawn as blue, although of course in reality they're far too small to have an actual colour. And the electron has two fundamental properties to it. It has an electric charge, which means that it responds to the application of an electric field, and that's how we move them around. And but it also has a spin, which is a sort of little magnet that it carries around with it, which I've shown here in red. Don't worry too much about the term spin, it's perhaps slightly misleading, but remember that the electron has this little bar magnet attached to it. Conventionally, we really use the charge of the electron to transmit a signal. That is to say, we generate a local excess of electrons over the normal density. And we punt that little lump of electrons down the wire using an electric field, and that lump of electrons stays together to some extent, and it spreads a little bit while it propagates, but then it's detected at the other end, very much like the wave on the rope. And this is quite energetically costly, and as I'll say in a moment, we may be able to find better alternatives. But of course, we also want to process information as well as transmitting it. And that brings us to the birth of the transistor. So I've shown this picture before. It's an elementary device which allows the computer to rewire its own circuitry, in some sense effectively deciding which calculations it is going to do on the fly, as it were, as a result of the outcome of previous calculations. And that, of course, makes it much more of a thinking machine, if you like, than a simple telephone exchange. This is the fundamental circuit symbol for the same component. There have been actually many new transmission technologies over long distance since the telegraph. You might be thinking, well, aren't we using optical fibers for all this now? And the answer is we are for long distance transmission, usually up to within about 50 yards of your house, and then it goes back into a copper cable, which is a bit unfortunate, but I guess we'll get that infrastructure thing fixed over the coming decades. But I really want to talk about the transmission inside the microchip, where we are still moving signals around using these little pulses of charge in exactly the same way, actually, that it was done using with the telegraph in the mid-19th century. So the question is, can we do better? And if so, how would we do better? So this brings us to the question of why do we want to do better? Why does your laptop need a fan? And the point is that this is the inside of a laptop. You can see that actually a fair amount of the inside is taken up by this cooling apparatus, and that's just for a small computer. When we come to huge data centers, such as the Utah data center, of which a plan is shown here, you can see that there are power substations all over the place, as well as the data halls themselves, and there's quite a lot of the floor of the area of this data center given over to cooling. Because a lot of heat is generated just moving around the packets of electrons that are actually carrying the signals in these data centers. And as I pointed out before, that's already a few % of the global carbon budget, and it looks likely to increase over the coming decades. So can we do something else? And this brings us to the idea of spintronics. Let me start with a simple and slightly misleading analogy. Imagine I want to pass a message through a swimming pool. I'm using a swimming pool because the electron fluid in a metal is a bit like a liquid. And so when we try to pass messages through metals, you can think of it as the problem of effectively trying to pass messages through a fluid. Now, one thing I can do is to blow bubbles through the fluid, and this is a bit analogous to transport by charge. It's energetically very expensive because to create a bubble, I have to create the surface of the bubble, and that costs a lot of energy because of surface tension and this kind of thing. So it does actually take a fair amount of work to create bubbles in a fluid. And you know this because when you hear a pan of water boiling, you can actually hear the water boiling. What you are hearing is energy dissipation from the creation and the popping of those bubbles. Now, okay, they're not really transmitting a message from the bottom of the pan to the top, but still, if you were transmitting a message that way, you'd be paying a lot of energy you didn't want just to create the bubbles at one end and to destroy them at the other. There are other ways of passing messages in fluids. This is a coloured dye diffusing throughout a fluid, for example, and this is a lot more energy efficient because you don't have to create all those phase boundaries, all the sort of edges of the bubbles, and you don't have to destroy them at the other end either. And yet in principle it works as well as a method of transmission. So is there something we could do in the electron fluid which would be more like transmitting using the dye and less like transmitting using the bubbles? And the answer is yes. We can try to encode the information not in the charge of the electron, but in its spin. So here on the left, I have a little cartoon of what's happening when we pass a conventional current, like in a telegraph wire. We have some of the electrons whose spins are pointing up, some of the electrons whose spins are pointing down, right? They're pointing in random directions. So I've said that's 50% up and 50% down. And both of those are flowing from the message sender to the message receiver, which means we are actually physically moving charge through the wire. And it's that that costs the energy, basically. There is a clear alternative possibility, which is that we could pass a signal by moving the upspin electrons in one direction down the wire, and at the same time, the downspin electrons in the opposite direction. This is called a spin current. And if you think about it, you realize that the net motion of charge in a current like this is zero, because the charges that are moving to the right in the top row are balanced by the charges that are moving to the left in the bottom row. And so the majority cause of heating when electronic devices operate is removed by this choice of spin currents rather than charge currents. The dissipation of heat doesn't go to zero, but it's reduced by a dramatic factor, several thousands, tens of thousands, according to relatively simple back of the envelope estimates. So if we could switch to transmitting our information within microchips particularly, and doing our information processing via spin currents rather than charge currents, we really could stand to make a big saving. We would then, of course, need devices, the equivalents of transistors that operate for Spintronics, but there are already sort of working prototypes of these things where you get ferromagnetic materials, non-magnetic materials, make them into sandwiches, and they, for example, allow one flavor of spin to pass through freely and the other flavor is strongly resisted, and this allows us to filter the electrons according to their spin direction, which would allow us to inject mainly spin up or mainly spin down electrons into a conducting channel. There are also designs for a spin transistor, so a version of the transistor which operates with spin currents rather than charge currents. There are not really perfectly functioning prototype devices of this yet, but work is ongoing, and I think we can be reasonably hopeful. There are also materials in nature which are part of this so-called quantum materials family, which naturally process the spin of the electrons. So a topological insulator is a material which has, among its other wonderful properties, the fact that at its edge, naturally, because of the physical properties of the material, electrons with their spins pointing up go one way around the edge of the material, whereas electrons with their spins pointing down go the other way round. This is called a chiral edge state, or a helical edge state, perhaps we should better call it. And you can see that it acts as a natural spin sieve. If I inject electrons into the side of this material, naturally the upspin ones will go one way and the downspin ones will go the other. So these materials could be very important spintronic components. So that's a new transmission method. We might be excited by this and ask, well, can we even do the processing differently? A spin transistor is exciting, but perhaps there are more exotic things we could do in processing information. And this leads me to the last thing that I wanted to mention, which is, of course, quantum computing, which everyone's heard about. So quantum mechanics tells us three things about the natural world. It tells us that the world is quantized, so some systems absorb or emit energy only in fixed size packets called quanta. So, when I absorb light, I actually absorb it in little lumps, not continuously, as the 19th century theory would have told us. It tells us that there is uncertainty. Some properties of a particle, such as its position, can be indefinite. You can think of that as the particle being in more than one position at once. That's a useful heuristic, although of course you have to work through some potential contradictions there and realize that they're not contradictions after all. And really importantly, there is a third thing, which is entanglement. When in quantum mechanics, when we consider several particles, we can't always describe the state of one independently of the state of the others. And it turns out that that entanglement, which was viewed for many decades as a sort of interesting quantum weirdness, is actually also a computational resource. You can use entanglement to do kinds of computation with quantum systems that would not be possible even in conception for systems described by pre-quantum theories. So quantum computing is that. It's entanglement-based information processing. And here's an example of a recent prototype quantum computing chip from the D-Wave company, whose name you see here. Other quantum computing companies are available. And this allows us to develop new components and to develop entirely new types of circuit, which instead of acting on these electrical signals transmitted in wires, be they electronic or spintronic, act directly on the quantum state of these so-called quantum bits, qubits, which might be the spins of nuclei doped into silicon. They might be little superconducting circuits. What you actually make these quantum bits out of is still a hotly contested topic, and people are developing all sorts of competing technologies. And quantum materials are also playing a very important role in providing candidate physical substrates for these quantum bits, which will be the workhorses of the next generation of quantum computers. I've put a couple of quotations here, which I won't read out to you in full, but this is just John Preskill in a recent paper talking about where we are now. So we now already have noisy intermediate scale quantum devices, NISQ devices they're called. So quantum computers with 50 to 100 quantum bits. We've already had fairly convincing demonstrations of those computers running faster than our best classical computers on certain types of calculation, but they can't do all types of calculation at the moment. And so we haven't really finished the quantum computing revolution by any means. However, as Preskill says, we should regard this as a significant step towards the more powerful quantum technologies of the future. And this quotation is pointing out that it's really entanglement that is driving the really new computational power here, and it's entanglement that we're trying to build into this new generation of materials in quantum materials research. The time for the talk, and I do want to leave plenty of time for your questions. I note that the era in which computing was developed in the 20th century was characterized by an unusually strong collaboration between quantum theorists and materials physicists. So the people who were growing the materials understood the new quantum theory, and the people who were working on the quantum theory were interested in the problems raised by the quantum description of the interiors of materials, and they talked to each other a lot. The result was silicon, the workhorse of the transistor revolution, and the transistor itself, and all the miniaturization that came with it. And some of this was done in universities, some of this was done in companies such as the Bell Telephone Laboratories, and there was active and vibrant intellectual exchange between those two settings. We're now again seeing that happen in quantum computing theory and technology, including quantum materials. There are more and more private companies putting work into quantum computing, and there's a lot more cross-hiring going on between industry and universities of people who work in the quantum materials and quantum technologies area. We don't know what the resulting Silicon 2.0 will be, the material substrate of the next generation of computers. But finding, understanding, and working with it will be key to a successful large-scale quantum computing. And that's one of the prospective applications of the current research in quantum materials, in which, among many other institutions, St Andrews is playing its part. Okay, I hope that's provided some food for thought at least, and food for questions, for which, over to you.
Thanks, Dr. Hooley, very much. I think I've learned more in the last 20 minutes about physics than I learned in 5 years of doing GCSE. So thank you very much for refreshing my knowledge in that way. We've had a couple of questions. One anonymous comment: I like the idea of bubble language. So did I. So thank you for that. And we've got a question from Varun, and also an anonymous question, which I'm going to bring together. So from Varun: so if we develop spintronic transistors, we won't have to supercool quantum computers? Question mark. And then how do you see the technological deployment of quantum computing panning out? Will everyone one day have quantum computers in their pockets, or will they remain rather large and specialist machines, as in the classic mainframes of the past?
That reminds me of a quotation I've heard attributed to Yogi Berra. You know, predictions are dangerous, especially about the future. Nonetheless, let me have a go. One thing I should make clear in answer to the first question is that a device that operates using a spintronic transistor is not a quantum computer. It is a classical computer where the classical computing is being done in a more efficient way, exploiting quantum materials. So it's not, I wouldn't call any computer that contains quantum materials as some of its components a quantum computer. The spintronic plan is actually to do rather conventional computing, but to do it in a more energy efficient way, avoiding all this heating that comes from passing the information using electric charge. Quantum computing is a next step, which is actually to replace the transistor entirely with other types of component which exploit the quantum nature of the electron or whatever it is, not just to transmit the information, but also to process it. That's really a step beyond spintronic computing and spintronic information transfer. Now, where do we see these things ending up? Well, this is so dangerous. I can imagine this video being played back already in 10 or 15 years and this answer being completely wrong. But nonetheless, let me tell you what I currently think. If we manage to develop relatively low cost, relatively scalable spintronic materials and devices, I would imagine that they would start turning up everywhere. So everywhere where we currently do information processing by moving charge around, we would do information processing by moving spin around instead. That would involve replacing the microchips that currently appear in all computing devices with spintronic versions of microchips, where instead of charge carried along gold wires, you had spin pulses carried along whatever we decided we needed to make those wires out of. And instead of transistors processing those signals, you would have spin transistors of the type that I showed in the talk processing those signals. But fundamentally what the computer was doing would be exactly the same that it's doing now. It would just not be getting so hot while it did it. And then, yes, we could imagine then shutting down all those big air conditioning plants at data centers, and everything could just sort of run at room temperature without overheating, which would actually be quite a significant energy saving. Quantum computing is very good for certain things, but it is not better than classical computing for every task. So, for example, if I want to crack our current security encryptions, RSA and so on, I definitely want a quantum computer, although presumably as soon as it becomes publicly known that that cracking has happened, we will stop using that form of encryption. If I want to search very large databases very efficiently, I want a quantum computer. So there are certain specific tasks at which quantum computers are very, very good. Would it be practical to have that kind of computing technology in your phone? Well, Technologically, it seems very difficult to do because these quantum computers are very fragile, and at the moment we know of no way to operate them except at incredibly low temperatures in most cases, or with huge amounts of architecture surrounding them to do the actual processing. You know, the amount of stuff that you have to plug in to that quantum chip I showed you to make it work is still basically a room full of kit, even now. But, you know, that's where we were with classical computing in the 1940s. And developments in 30 or 40 years brought us to a level of miniaturization that I think nobody in the 1940s was seriously envisioning. So Spintronics in your phone, I can definitely believe if we find a good set of material candidates and they turn out to be reasonably industrially processable. Quantum computing in your phone, I currently find rather less likely, but, you know, all sorts of predictions like that have been wrong in the past, so please take it with a pinch of salt.
On behalf of the audience, thank you very much for taking the risk, Chris. Thank you, greatly appreciate it. Just on those questions, what tasks quantum computers are good at and what they're not good at and why? We've had a couple of anonymous questions on that. Why can't quantum computers not do certain computations that conventional computers can do? And a second anonymous question, which classes of calculations are and are not possible with quantum computing now, and why is that?
Right, superb questions. Let me try and remember the second while I answer the first, but David, I'll ask you for a reminder if I seem to have forgotten. So the first question was why can't a quantum computer do everything? It's not that it can't, it's just that you don't get an advantage from a quantum computer with many types of task. And to understand why that is, let's think a moment about how a quantum computer is different from a classical computer. The essence of it, and apologies to any experts listening for which this is a real cartoon, but the essence of it is to exploit this feature that I mentioned, that quantum systems can be in more than one state at the same time. That means that if I take a quantum computer, so let's think of a simple task like adding two numbers. If I take a quantum computer and I prepare its input registers with 3 and 4, and then I run it, it adds those together, and in the output register it puts the number 7, assuming it's working correctly. Then I could run it again, and in the input registers I could put 5 and 12, and it adds them together and it outputs 17. But since it is a quantum computer, I could also put the input registers in a quantum superposition of 3 and 4 and 5 and 12, and then the output would be a quantum superposition of 7 and 17, the results of the two calculations. Now, in a sense, that's really powerful because I've done two computations in the time that a classical computer would have taken to do one. And of course, I could prepare my input registers in a superposition of 1,000 calculations that I'd like to do. The quantum computer does them all at once, and all of the answers turn up in a quantum superposition in the output register. So that's where the advantage comes from. Now, the problem is, of course, when you measure a quantum system, you collapse those superpositions. So if I actually go and look at the output register, I will only see one of the answers, and I don't know which one it's going to be. So although the quantum computer has done the 1,000 calculations I wanted, I can only read out the answer to one of them, and I don't even know which of the 1,000 it's the answer to. So that's the fundamental problem. What you have to do is to try and build algorithms for these quantum computers where you use the fact that it's doing many calculations, but you let it feed back on itself and amplify the result that you're looking for and suppress all the others. That's why it's good at searching problems, because the quantum computer can kind of search everywhere at once. And when it finds the thing that you're looking for, it can amplify that location in the output and suppress all the others. So there are real kind of exponential speed ups from this kind of quantum computing for problems that involve searching. You know, like prime factoring large integers is essentially a searching problem. searching for an object in a large database is essentially a searching problem. That's the kind of thing that quantum computers are good at. In principle, they're really good at everything, but you can't read out the answer, so it doesn't really do you any good. What they're useful for is problems where you can convert that massive quantum parallelism into a proper readout. And the other question, sorry, David, I'm aware I'm going on a bit, but I'm trying to answer these properly. So the other question was, what can quantum computers currently do? And why is it really those things that they can currently do? Currently, actually, the demonstrations of quantum supremacy, which is a quantum computer doing something provably more efficiently than a classical computer could do it, are confined to even simpler tasks than the prime number factoring or the searching that I just described. And the reason for that is essentially that at the moment we don't have programmable quantum computers, at least at the scale of the largest devices, which means that what people are currently doing is building demonstration devices where the computational problem they solve is basically hardwired into the machine, at least to a large extent. And those have been good as demonstration pieces. There was some very significant publications from Google last year about quantum supremacy, and they've been somewhat contested, but actually I think it's basically right. I think quantum supremacy has been demonstrated for those particular tasks, but they're slightly arcane tasks. They're measuring particular properties of certain probability distributions. So the next step is to kind of get beyond the noisy intermediate scale quantum devices, get something more programmable, and then hopefully we can demonstrate quantum supremacy in some of these approximately real world tasks like database searching or integer factorization.
Thanks, Chris. That was a superb answer. Thank you very much for that. We're getting a lot of positive comments, and I'm also very aware that we're kind of running into the last 10 minutes or so of the Q&A. We've had a lot of questions on whether or not the energy currently consumed by computation, whether if we replace conventional computing with quantum computing, whether that will just lead to some other bigger problem that we may or may not be able to foresee at this point. So I'm going to ask Lorna's question here. If heat is the downside of present day computers, what might be the downside of quantum computing?
Yeah, that's a great question. So obviously this verges into a more political territory, right? Even if we can do this, do we want to do it? And that's a perfectly proper question and one that I'm happy to express views about. One potential downside for spintronics and quantum computing is carbon cost of production. So of course I've said that if we have these spintronic devices and they're running, then the energy consumption is much lower. But one also has to ask about the questions of, what's the carbon footprint of producing these spintronic chips compared to conventional chips, or what's the carbon footprint of producing a quantum computer relative to a classical computer? Now, obviously, in the early stages of most new technologies, the carbon footprints are high, and then they come down over time as people look for ways of making the technology at scale or more efficiently. But of course, production at scale can also bring its own carbon footprint problems and other pollution problems. So without knowing really what the substrate material would be for this candidate technology, it's very hard to say whether the carbon footprint of producing these things will be outweighed by the carbon saving of running them. And obviously, if it isn't, we might want to think twice about going down that line. But we're in such early days of research into it that I think we can't answer that question at the moment. And it still seems to be worth looking at in case we get lucky. It's also worth pointing out that so the Centre for Design of Quantum Materials has a Centre for Doctoral Training attached to it, and one of the things that we do with the students in that centre is to talk explicitly about these questions around responsible research and innovation, around thinking about eventual technological applications, and thinking about whether we're doing research into a material that is so rare or so toxic that it could never really be the substrate for a technological application. So I think there's more awareness even in the sort of blue skies research community now that if you have to break a tie between two materials, then go with the one that looks like it could actually be deployed. And that sounds obvious, but it's something that we're trying to make more explicit in the training for the students now than we used to. The other potential downside, which I think is important to mention, is there's this famous phenomenon that you build more roads, you get more traffic. so you improve the roads, you think this will be great for existing drivers, and then what actually happens is more people switch from public transport into cars because the roads are now better, and you've actually made your pollution problems worse. You can imagine something like that going on with increasing computing power. I mean, we are spending huge amounts of the world's carbon budget at the moment on processing data. And what are we doing? We're showing you a very high resolution picture of me sitting in the living room of my flat. we're pumping carbon into the atmosphere to show you a static picture of my clock and some of my pictures on the wall. And there's no point to that. We're just doing that because we can. And so I think there's also a risk that providing technologies that can do essentially economically useless activity, except for the people who rent the technology to you, can encourage the development of essentially economically useless activity. And quantum computing will be no more immune to that law than anything else.
Thanks, Chris. I just want to say we've had a lot of really interesting technical and even philosophical questions from people that we're simply not going to have time to ask her, but Chris has very kindly said he's happy to take those questions emailed to him, and we're going to pop his email address into the chat as well. I'm going to ask, we're also going to put a survey into the chat. So if you've enjoyed today, got some suggestions for improvement in how we conduct these talks, or you want to just comment on them and let us know about start times, things like that. It'd be very helpful if you fill in the survey as well. So I'm just going to ask a final question now, which is anonymous, and going back to the potential ways of transmitting information within current infrastructure. Are electronics and spintronics the only two options of transmitting information, or is there a third, or is there a number of other ways?
Yeah, that's a really interesting question. So if you want to move information around using electrons, then essentially the electron only has two properties individually, its charge and its spin. So you basically have to encode the information in one or other of those, or a combination of them. However, you could also imagine not trying to encode the information in individual electrons organized into these little wave packets, but you could encode it in structures in the electron fluid. And an analogy for this might be smoke rings. So of course I could communicate with you in Morse code using smoke rings. A smoke ring is not an individual air molecule. It's a collective structure of kind of rolling bits of the fluid. And those structures exist in quantum materials as well. So for example, if I take certain types of superconductor, which is a form of quantum material, those superconductors have vortices in them where the electrical currents kind of run round in a ring. And those vortices can be quite stable objects. I could imagine encoding information in aspects of the vortices in superconductors and transmitting it that way. And there are various other kind of collective phenomena that happen in quantum materials which could be used for the encoding and the transmission of information rather than encoding it at the single particle level. Now, of course, that would reduce the density of information that you could pass because these collective objects are relatively quite big, but it might increase the stability, and potentially it could also increase the speed, depending on exactly the quantum material that you use and exactly what we discover in the quantum materials area in the coming decade or two. So there are these more theoretically interesting, perhaps, proposals for how information might be encoded or stored via collective excitations of the electron fluid rather than via individual electrons themselves. And that's all at a very early stage. But for example, things like so-called skyrmion racetrack memory are already a kind of getting towards an industrial proposal for how information storage might operate using these collective excitations, but maybe information transmission isn't too far behind.
Thanks, Dr. Lee, and on behalf of the audience, I'd like to thank you for a fascinating, very generous talk. I'm sure it was greatly appreciated. If people would like to take part in some of our other events today, the program is at the top of the chat bar. You can have a look what else is on. And we also put all of our Saints talks up on our YouTube channel and on the Alumni website. So you can browse the ones we've already done and also have a look at what's coming up in the future. You can also follow us on our Facebook, Twitter, LinkedIn and Instagram channels. Thank you again for joining us this morning. I'm just going to hand back over to Dr. Hooley to say thank you and goodbye.
Well, thank you very much, everyone, for coming. Thank you for your excellent questions. Please don't hesitate to use the email address provided to send more. I'm very happy to discuss anything in this talk. And thanks again to the organisers for inviting me to speak.